Thanks everyone for coming to the final session of this calendar year. Hope everyone had a good Thanksgiving. It's been a few weeks since we last met. And today we're going to have Taylor Childers present about data pipelines in deep learning. But first, I'd like to share a few slides that were given to me by the educational department to give some opportunities, information on opportunities that are available for you to continue this type of work in a research setting and get some experience over the summer or perhaps over the fall and the school year. Okay, can you see the slides?
Yep, they look good.
Okay, so right now the lab is currently in a virtual setting, so as of right now, these research experiences would be virtual, but if they are in person, you have a lot of great social activities and networking activities and scientific talks, and a lot of that can still happen during virtual internships. And these are some examples that you have right here. And I personally was an undergraduate intern about 7 or 8 years ago, and led to me returning here after I finished my PhD, so I can personally vouch for the high quality of these programs. Here are some examples of summer programs that are available to both undergraduates and graduate students. So the Givens Fellowship and the W.J. Cody Fellowship are open only to undergraduates, but research aids can start kind of any time and are open to both undergraduates and graduate students. These programs are specifically for the summer and are only open to undergraduate students, and the application process goes through the Department of Energy, not just Argonne. Here are the program dates. Usually, like I said, starts in the summer, and the application deadlines. If you have any questions about this, you can refer to the slides that I posted in the Slack channel, or you can message any of us for more information. And here are grid links if you ever need more details about them. Okay. So as mentioned, today's speaker is Taylor Childers. He's a computer scientist in the data science group within the ALCF. He'll be speaking to us about data pipelines and how we can make the CPU and GPU really work together for these deep learning algorithms that were discussed in the last session, or even traditional machine learning algorithms that were discussed 2 sessions ago. If you have any questions, please join the new channel on Slack. That's 03 Pipelines for DL. And all questions can go there. And also be sure to go to the GitHub link, which I'll post again. And if you have the repository already cloned on Theta, which you should, be sure to run a git pull command to get the latest changes, since we were changing it up until 30 minutes ago or so. Okay, Taylor, are you ready?
So I'll be talking about CPU side data pipelines. So a lot of the HPCs that you're going to see now and in the next 5 years are going to be hybrid machines that have a CPU and a GPU, if not a couple of GPUs and many, or 2 CPUs and many GPUs. So there's quite a few resources to keep busy and ways to improve your throughput. When we think about machine learning, usually we think about the side of the building our model, running the inference and the backpropagation. But it's also important to consider how are we building our data. In many of the simple examples that we cover in this tutorial, they're very small data sets, things like MNIST or CIFAR10 can sit in memory. They don't take up a lot of resources, and we don't have to think too much. We can just operate on the full data set without much consideration for where it lives or where it needs to move to. But there are going to be cases as you get into more advanced work where you cannot load the full data set all at once. So you have to be processing it in real time. And so that's what we're going to talk about today, how to do that and take advantage of the resources that you have. We'll be using the Imagenet example. So here I'm just on the README under the O3 data pipelines. A lot of what I say will be captured here in this text. And we're going to be using the Imagenet data set, which is a very well-known data set. It is the data set that had previously been used during the Imagenet AI challenges that sort of drove the advances in AI in the early 20-teens as various companies competed to do the best in predicting what was contained in the images. So we're going to start with this notebook here, which is down in the TensorFlow directory. It's called inspect pipeline. And actually, I'm going to start this live. So I'm going to go on to jupyter.alcf.anl.gov, and I encourage you to follow along. So I'm going to log into ThetaGPU. Okay, so Imagenet is a data set of images. They're JPEGs. There's 1,000 different classes of objects in the photos. And when I say that, I mean, obviously the picture has other things in it, but there are target classes for each image. And most images, though not all, have a corresponding XML file. Let me zoom in here again. They have a corresponding XML file that contains annotation information, specifically a bounding box that tells you where in the image the object is located, in case you're interested in training networks that predict bounding boxes for objects, things like the YOLO network. YOLO stands for You Only Look Once. It was one of the first networks that processed full images in parallel with bounding boxes. Although I don't think it's leading edge anymore, but at the time it was definitely, everyone was excited. Okay, so I think actually I want to change my kernel. Actually, I think we'll try with the base. We'll see if that works. Let's see if the Python 3, you can always see which kernel you're using up here at the corner. And we'll try with Python 3. I think it has everything I need in it. So we're just going to load up some tools. Oh, it doesn't have matplotlib. Okay, so we're going to change our kernel to the Conda kernel. We're going to wait for that. Okay, kernel ready. So now I'm going to restart. Okay. And I have a JSON file in this local directory that just I use for configuring the example files. So I'm just going to load up that JSON and I'm going to print out the configuration information you can see here. And the important thing here is to see where this file list is located. Because this text file is literally just a list of all the JPEGs with their full path, one per line. So I'm going to read that in here. So I'm going to grab that file name. I'm going to open it. I'm going to read in all the lines. I'm going to print off how many lines there are. So that's how many files we have. I'm going to choose one. And I've been specific here. I've kind of poked around a little bit to find an interesting example. And then I will print the file name that we chose. I'm going to read in the image data. And then I'm going to use pyplot to show you the image, which actually you can already see to some extent. So there we go. So you can see the data set has a little over 1 million images, and where it lives on the one that we picked, which corresponds to an index of 4,000 in the file list. See the file name, printed the data shape. So this is the image is 332 pixels by 500 pixels with 3 color channels. And then I used PyPlot to show you what the picture is. The next thing that I'm going to do is I'm going to convert this file name to point at the annotation file, which really just means I'm going to change this from data to annotations and the JPEG to XML. So you can see where I do those string operations here. And I'm going to make sure that that file exists. Like I said, not all of the images. Some of the images are so cropped in on the object that you don't need a bounding box. You just assume that the full image is the class object. And so I'm going to run that here. I also print out the XML file just so you can kind of see the content. So you can see this is the annotation file. This tells you the sort of the class label. They use this weird numbering scheme that's not even from 0 to 1,000. I'm not sure why they decided this, but in any case, it tells you the size of the image, and it gives you some information. So it shows for each object in the image, it gives you a bounding box in pixels. So you get the X min, the Y min, the X max, the Y max. So you get all this information, all the bounding boxes, and we want to parse that XML and extract extract these bounding boxes. So I'm going to use some of the built-in tools in Python for reading XML. XML is a bit of an antiquated format, in my opinion, but it's also widely available, and tools for reading it are widely available. So it's probably one of the reasons they use it. And so I'm just digging in here, and then I'm gonna do this find all the object. And remember this keyword, it's all based on these keywords here and these brackets. So when I do find all the objects, it's returning a list of all these things that are bracketed by the object keyword. And then I can loop over those objects in a similar way to, in a nice Pythonic way. And for each object, I want to find this bounding box keyword. And then I want to extract these coordinates, the X min, Y min, X max. And I convert those to integers, make them into a list, and append that to my list of bounding boxes, which I created here. I'm going to print those boxes, which you can see the coordinates I extracted. And I'm going to plot everything on the image. So again, I show the image, and now I'm going to build these rectangular objects that Matplotlib knows how to interpret. And I'm going to add those to the image. And you can see the boxes here. They outline each of these, I guess, berry class objects or fruit. I'm not sure which. And you can see it nicely highlights all the objects in the image. So some of this code is implemented in the script that we're going to take a look at, Python script that we're going to take a look at. I just wanted to give you a better feeling for the data that we're playing with. Feel free to go in here and change this index. Okay, there's a different one. Let's see if it has an XML file. It does not have an XML file because it's fairly well cropped on the object. Let's see if we can find another one. That one's probably not going to be. Let's see. Okay, so here we found an XML file. In this case, the object pretty much takes up the whole image. Let's see how it looks whenever it's all plotted. You can see the bounding box there for the single bridge object, I assume. This is a category of bridges. So that gives you an idea of what's contained in the data that we're going to be looking at. So I'm going to go ahead and I'm going to kill my job here so that I can start up another job elsewhere. So I'm going to shut down my kernel, go to my control panel. I'm going to stop my server so that the job actually stops. I'm going to log out. Okay. And so now I'm going to go back here. Okay. Here I'm just on the Theta login node. I'm going to make this a little bigger. Okay. Maybe a little too big. And so here I'm just on the Theta login node. I had already run the module load Cobalt GPU command. So make sure that you have logged into Theta, run this command, and then I'm going to grab an interactive node. So I'm going to write qsub-i. I want a single node, and I want my single GPU queue. 60 minutes is the limit. And then the project is ALCF AI TP. I'm going to go a little slowly here just so to make sure everybody's gotten a chance to log into the machine and get their job started. Please make sure you also did a git pull on the repo, because I think once you're on the GPU node, it's a little bit more of a task to run git pull. Okay. I think the network is, yeah. Network is a bit obscure when you're on here. Okay, and then I'm going to do module load, Conda 2021. I think there's an 1130. And then Conda activates. And so that loads up all the Python libraries that we care about, things like TensorFlow and Torch. Okay. And I'm just going to bring this up so that we can see the code here that we're going to run. So we're going to be running this script right here. And let's just take a quick look because we'll recognize some activities. So maybe we start at the top though. We start at the very at where execution begins. So I mean, I've got all these function definitions above, and we'll take a look at those. But down here in the primary main of the code, you can see some arg parsing going on here. So some command line arguments that you have that you can set, including the config file, which is the same config file we used as the notebook. So that will pass in and it will extract in a similar way the configuration file. I do have some hooks in here for Horovod if you want to see how multi processing would work. So if you were loading up Horovod, you would just pass the Horovod object in here that was imported.
What is Horovod?
Have we covered that yet?
We have not.
Ah, okay. Well, then don't worry about that. You'll see that later. For the most part, it's not in this code. I just wanted to put it there in case somebody, in case we were in that situation. So eventually we will cover Horovod, and you can, at that point, be able to see how to plug these in. Okay. And so the meat of it comes down here at the bottom, where we are going to call this get dataset function, and we're going to pass in that JSON config file. And then it's going to return a training data set and a test data set. So now let's go to that and take a look. We're just going to go through here kind of quickly, or not quickly, we're going to take our time and make sure everybody is on the same page. So we've got our data set, and we're going to initialize some global variables just because of the way the TensorFlow datasets works. I need some of these for our processing that you'll see later. So the first thing I'm going to do is I'm going to grab the crop size. So you may have noticed in the notebook that our data sizes for each image can change. So the Imagenet images are not all the same size. So we want, of course, to change that for any sort of machine learning activity, because our models always expect the same number of inputs. So in the config file, I define a crop size. I'm pretty sure it's 256 by 256. So that's we're going to use that later. And then I extract the training file lists. I make sure that they exist. And then I have this function, which we won't use in this example, but I wanted to include it for completeness, which is essentially takes all those strange IDs that the data set includes, the N plus the 6 or 8 digit number. I don't remember what it was. Actually, I guess I could go back to here and duplicate this. Takes that long digit number and turns it into just a 0 to 999. So it turns it into unique labels. So here we go. So this is sort of the class label for this file, which is not very helpful for machine learning tasks. So essentially this builds a lookup table that says, okay, I have this string. What class number am I? 0 to 999. So it's just a mapping from that to that so that I can train on it. But like I said, we don't use that in this case, but you would need this if you were building out or if you were doing your training. So now we go into this build data set from file list. So here I'm just passing in the JSON config file again and the training file list or the test file list. Okay, so we'll go down to that. So this takes those two things. It mainly relies on the data subset of the configuration file. Here again, if you were using MPI, which we're not going to talk about, you would need to think about this, but I'll just leave that there. Okay, so we saw this in the notebook. I'm going to open that file. I'm going to read in every line and then build out my file list. Here, I'm just trying to provide some feedback to the user so that they know roughly how many batches they're going to be iterating over. So it's just a quick calculation based on the batch size. It comes from the configuration. So I have my file list, which is a bunch of strings with full paths to the JPEG files. Now, in TensorFlow, I can immediately create a dataset object that's from that Python list. And so this is now a vector of strings that point at files, or they have file names. Skip this MPI bit here. And so the first thing we're going to do is we're going to shuffle that list. So whenever you're doing machine learning and you've got your data, you always want to shuffle your data so that you're not just training in the same order all the time, because your network can actually learn the order of your data and just start making predictions based on the order of the data. So we always want to shuffle our data. And since our data set is too large to fit in memory, this isn't like, if we were doing it in a slightly different way, where we loaded everything, where we were loading images, not the file names, right? I can fit all the file names in memory on a single machine, but I could not fit all the image data in memory on a single machine. So we actually win in this case because we're actually just shuffling the JPEG file names, which allows us to shuffle the whole data set together. Whereas typically what you do, or if you were actually dealing with data that fits, that doesn't fit into memory, you would have a shuffle buffer size. And so even though you're not shuffling the full data sets all together, you would still be shuffling chunks of the data set, and that would be reasonable enough to get you the performance that you need in your machine learning application. So usually you specify a buffer size. So this is really like how much memory does TensorFlow set aside to load data, shuffle it amongst itself that's loaded, and then start building batches out of that data. Okay, and here I'm just telling TensorFlow, yes, at the end of each, after I cycle through the entire data set, reshuffle again. So essentially, when we're talking about epochs in training, one epoch is one step through the full data set. When you get to the end, you want to shuffle the data again, not have the same order every time. So I'm shuffling the file names, and now I'm going to call this map function. And notice how, so the first time I created the data set, I did it this way with tf.data dataset from tensor slices. So now I have my dataset object. I'm being a little sloppy or lazy here because I'm literally just replacing my Python list of strings with a dataset object, and I'm overwriting the object in memory. So just be aware of that. And I keep doing that. So my shuffle returns yet another instance of dataset of a TF of one of these objects. And so each time I call this, I'm creating a new object and replacing the old one. And so here I'm doing the same thing. Map is a function that executes a function that you specify here on every entry in your data set. So it's a way of converting, it's a way of mapping or converting data from something to something else. So in this case, I'm going to call this load image label and bounding box function. So this is where the meat of the program comes in. And so if we go down here, this is going to operate on a single image path because the function is being applied to every entry in my dataset tensor, right? Which is really just a list of file names. So this function is going to get one file name. If you have it set to debugging, it will tell you what file name that is. And now it's going to split this file up. It's going to do some parsing so that it can build the XML file name. Remember, we need to replace some of the pieces of the string from the JPEG file to the XML file. And so once I have the annotated file path for the XML, I'm going to call this function get bounding boxes and pass in the annotation path. It's going to return a float object and an integer object, which is the boxes and the indices. So if we go down here, hopefully this looks a little familiar from our notebook where I'm parsing the XML file. I'm getting my bounding box. If I don't find a file, a corresponding file, the full image will be the bounding box. So it still returns a bounding box, but just one. So then I can convert those things to NumPy arrays, things that TensorFlow can parse. And then we come back. So now we have our bounding boxes, we have our box indices. And now I'm going to open the JPEG. So I read in, I use TensorFlow's IO library to read in the image. I am going to use its tools to decode the JPEG, tell it that it has 3 channels. This isn't like a black and white image, it's a full color image. That's why the channels here is important. And then I'm also going to expand the dimension here so that I can add a batch, right? So this image has a shape that's just the image. It's width, height, and channel. But I'm going to start stacking these together to build out batches. So I need to add in the dimension here. And so at after this step, the image is really just 1, the width, the height, and the number of channels, which is 3. I'm going to run here. I'm going to crop and resize the image to that crop size that I set earlier, the 256 by 256. I'm going to convert the image to floats in the range of 0 to 1. So here I'm just, instead of having the 3 color channels represented as integers from 0 to, I think it's 255 for JPEGs. It's just going to be from 0 to 1, which is much more friendly for machine learning. Let's see. Oh, actually, sorry. So in the crop and resize here, notice I'm passing in the bounding boxes. I'm actually being a little lazy here in the sense that what I'm actually telling TensorFlow to do in this case is take the image, use these bounding boxes to chop out the little piece that is the bounding box, and then crop it to the size that I specify. And what this does is, instead of having to run something complicated like YOLO, and I see Kyle posted a link to YOLO in the chat, so feel free to take a look there. If you don't want to run YOLO, you want to just do something simple like straight up image classification, 1 class, 1 image. You can cut out around the bounding box and try and train just on the content of the bounding box. So that's just an example there of what one way you could simplify the problem if you wanted to start out a bit simpler. And so here I am taking the label, which is coming from here, up here at the top. So I extract that label that looks like this, that tells me what kind of class is in the image. And I'm going to use my lookup table that I created, and it's going to look up that label and return the 0 to 999 class, index, right? Which is the thing we usually use for machine learning. We usually use, an indexed array, not something that's based on strings. Let's see, let's duplicate later. All right, so in here, in the case of Imagenet, you'll only ever have multiples of the same object. So you notice in this image, it was the same object repeated over and over. None of the images have different classes labeled in the same image. So here, all I'm doing is I'm saying, I want to duplicate this label to match the number of images that I created up here. So if I cropped and resized based on the bounding boxes, and there were 5 of these berries, I need to make sure there are 5 truth labels for berries in my output. So now I'm pretty much done at this point. I've got my image data, I've got my truth labels that tell you what class is in the image. And so that's what comes back from this mapped function. So now I have a data set that has the JPEGs, it has the truth labels, and if I had cases like what you saw in that image, where one image became 5 because there were 5 berries or whatever in the image, I have to flatten that out, because what's actually been done at this case, this data set here, now has, for every file name, the number of images that came out of it. So what I want to do is I want to just flatten everything. And so that's what this unbatch, apply unbatch does. It just makes it so that there's one image, one label, all the way down. And now I'm going to call the batch command. And so this is really telling the data set, when you're doing training, what's the batch size. And in this case, again, it's coming from my configuration file. And now some more important pieces. There's the, so I want to, well, I'll do that anyway. Next thing I do is I do a prefetch, and I'll mention that last. And then I also added in at the last minute, because I just was finding this out, there is a way to control in TensorFlow the number of threads that these operations are utilizing. And so now let's talk about the parallelism here, right? So this is all code that's being executed one after another. But there are ways that even on the CPU side, we can parallelize, right? I mean, if you have a ThetaGPU node that you're using by yourself, you've got 2 CPUs, and both CPUs have, 30 or so cores on it. Each core can hyperthread. So I mean, you've got lots of options for parallelization. And one of the places we can do that in the TensorFlow data, the data model that they have, is this mapping function has a parameter called number parallel calls. And I have this set in my configuration file, which maybe we go back here and just take a look at it real quick. You can see it printed out at the top. So you can see, I set my batch size. I have my shuffle buffer, how much memory I want TensorFlow to set aside for this. And then whether or not it should shuffle every epoch. and then the number of parallel readers it should use. And so what this does is it will launch this function in parallel on the file names. So every file name is independent from each other. So there is no coordination that needs to happen here. They can all be opened at the exact same time. So how many should I run in parallel? Well, that depends on the system. And so that's why it's a setting here. And so this is one way you can control the parallel execution of your data pipeline on the CPU side. Another place that you can control that is in the prefetch. So this prefetch literally puts together batches of data even though you haven't asked for them yet. So if you have a really big data set and your batch size is 12 and you've got 1 million images, and so if your CPU is sitting around doing nothing while the GPU is busy doing your forward and backward inference and backpropagation on your model, you can use that time to prepare the batch that you need for the next step. And so that's what this is doing. It's saying, I want TensorFlow to preemptively build batches, even though I haven't asked for them yet. And I'll show you what I mean by ask in just a moment. And I can tell it how many to buffer. So, really you just need 1 or 2 here, because if you already have enough free time on the CPU to prefetch 1 batch, you're already immediately ready for the next training step. So, and then in this case with this private thread pool size, this decides some of the internals I don't fully understand, but I'm essentially going to set that to the same as the number of parallel readers. So these are the same. And we'll take a look at some of the details later. So that's, okay, so let's go back to here. So essentially at this point you return the dataset object, okay? This is the build dataset from file lists. And so we passed in the list of the training files that we wanted to use, which are separate from our test. And we get back this train dataset object and valid dataset object. And so those are the returns from this function, which is being called down in our main, down at the bottom, where we're passing arguments from the command line, and we call it here. So now we have our train data set and our test data set. So in principle, now you could start your training loop. You want to define your model, create an optimizer, create your loss functions, and then start your training loop. Now, I don't include any of the ML stuff here. There is a full example in another repo, which I mentioned in the README, that's based on the Imagenet running with ResNet, but I wanted to focus on the dataset stuff. Okay, so here, I'm just going to quickly run. So I have this command line setting number of steps we're going to run through, and it's just defaults to 10 if you don't set it. So it's really just going to loop over. It's going to ask for 10 batches essentially. Okay. So for I in n steps, and I'm also using TensorFlow's built-in profiler, which we will talk and cover probably much later in the tutorial series. but I'll show you some of the outputs so that you can visualize how this is looking on the CPU. And here I'm just using the Python iterable language here. I probably could have made this clearer by making this for entry, and maybe we can do that on the fly while we're here. But in any case, so this just allows me to get entries from the data set. So I'm going to start this for loop, and now I'm going to say, give me the next training data set, and it literally returns the stuff that was generated way up here, right here. So these are the stuff that the images and the labels that were generated from my image path. So now I have a batch of training data. My config file sets the batch size to 128. So there should be 128 images and 128 labels. And I just print those out here for us to see. I sleep for 1 second, just so that it's not too quick. And then here I calculated images per second, although I should have done that down after the sleep. But anyway, that doesn't matter too much. This is really just to give you an idea of the performance or how many images you're processing. And the sleep is to kind of simulate the time it would take for a largish, something like ResNet to run on a GPU. So it's the time that you have to build your batch, essentially. So imagine here, our GPU is running on a batch, doing the forward inference, calculating our loss, getting all the gradients and back propagating through the network. Meanwhile, the CPU is busy building data. And when you ask for your next data, that's when this is the ask right here. Okay. So by this time, we all have a GPU, and we're well into our 60-minute reservation. And just so you're aware, I want to go back here to the README file. And we're going to run this command right here. So this is assuming that you've already module loaded and conda activated. We're just going to cut and paste right here. So this runs the script that we just went through. I am explicitly forbidding TensorFlow to look at the CUDA device, the GPU, by including this environment variable prior to calling Python. And that's just because otherwise CUDA would do some preemptive preparation. It would copy our data to the GPU, and I wanted the profiling output to be very clean for you guys to see, so that it was clear the parallel versus serial. And so in this case, we pass it, we call the script, we pass the configuration file, and then we tell it we only want one parallel reader. So there's really it's not parallel. And we don't want it to prefetch anything because we set the prefetch buffer size to 0. It takes a little bit to load up everything off the shared file system. Plus, if we're all doing it at the same time, helps slow things down. And so here you can see it's looping over the data. It got our input, our shape, which is the batch size. our cropped image size, which is 256 by 256, and the 3 color channels. And then we also have our labels. There's only one label per channel or per image, so it's just a list of 128 integers, which I am printing here. So this is the 128 class labels you can see, and I do this 10 times. So we loop over 0 to 9, calculate our images per second. It's fairly slow because I forced it to be serial. And I was talking about this TensorFlow Profiler that I put here so that we could see. And so it's going to automatically load up the latest run that I made. And you can see how it's laid out all the TensorFlow operations. I'm going to try and make this as big as I can based on their interface. But essentially what you see is the main Python process up here. And then you see the thing here in the middle is controlling the data set creation. So it's not doing any data processing, it's just controlling the creation of the data set. And here is a process that's actually doing the data loading and the batching, okay? And so each of these lines on this side represents a process that's running, okay? And I can use their interface to zoom in. You also get a time, so you can see the time. So you see 0 seconds at the start, 10, 20, 30, 40, and then it ends at 50 up here. And we'll zoom in, it even labels the steps, the training steps for us. So you can see I'm going to zoom in on train step number 5. This is all the various TensorFlow kernels that are being called. And then down here, remember, is where our data set's being created. And my guess is if you count up all of these things, if you were able to count up all of these lines, there's probably 128 of them, because that's how big our batch is. And so you can see calls like read files. So this is where the JPEG is being opened and processed. You can see the calls to some of our functions. Remember, convert to tensor. There's constant in there. I'll change this to that so I can move. So we get the read file. Read file takes the longest. It actually has to go do something, read data from a file system that sits in a separate cabinet with a network attached. So it's, it's not like sitting there right on your machine. So you have to go fetch it. That's why it's so long. It takes up so much time. Okay. And so let's zoom in over here. We can see the decode JPEG call, the crop and resize. There's a cast in there and a resize, another resize. So you can keep zooming in here and it'll show you all these calls that we made during our pipeline. And okay, I'm gonna zoom back out. So the important thing here was to see, this took a while. I zoomed out way too much. But you can see that we are running just as this single process here. Excuse me. So the next step is we're going to parallelize this. So we're going to take advantage of those parallel pieces that we had. So I'm going to cut and paste the second command from the README. And I include screenshots from that profiler so you can see those here. And you can see it's quite a bit faster. So you can see our image rate is up. And what we've done here is we've told it to run 8 parallel readers. And we've set the prefetch buffer to 2. And now if I go over here and I reload my profiler, go down here.
There's a question in chat about the gaps in the timeline.
In the previous one. Let me come back to that since I just loaded this up, just because it takes, a few seconds to switch between. So here you can see the same thing, but now we had our 8 parallel readers, and we told it to prefetch. So what you have now is we've got 1, 2, 3, 4, 5, 6, 7, 8 parallel processes running, all reading data. And now you can clearly see the break that happens. And there's probably a little bit in the previous one because of my weight, but we'll take a look. And so let's zoom in on the first one here, because obviously it's crowded here. You have to wonder why. So the first thing it's going to do is it's going to generate our first batch that is going to immediately get processed. But we told it to buffer 2 additional. So what you can see is all the processes are busy quite a while here, filling that buffer for us. And as we step through, so here we'll zoom in. No, don't go back. So now we'll zoom in. I think we can see that here. So you can see iterator batch v2. So these are the boundary markers for the batch creation. You can see all our read files taking place in all the processes in parallel. So it's taking advantage of the CPU. If you had the full node to yourself, you would be able to scale this out even more. Since we're using the single GPU queue, they have restricted how many CPU cores we have access to, so that since we're all sharing together. But if you were doing real science, you had a real big data set, you'd want the full node to yourself, and you could have 128 of these threads all running at the same time. So what you see here are multiple batches being prepared in the first iteration. Let's see if we can get our timer up here to show up. Okay, so you can get a little picture of how much time this is taking. Okay, so you see our kind of the start up here at like 2.9 seconds, and then the first batch looks, I'm assuming this is the boundary here. I can't quite make out a strip. So the first batch is taking about half a second. Looks like there's probably some initialization going on here, some time. Or maybe it's the shuffle here that's taking a little bit of time to get started, to load up and shuffle. So we wait for that shuffle to finish, and then we can start building our batches. And then in our second batch, which we'll just call it from here to here, is about 400 milliseconds. And we get another 400 milliseconds. And now we're seeing, I don't know why this isn't fully subtending here, but in any case, this probably marks the next request. So essentially our loop has executed. And so there was some downtime here that you can see. So between executions, our CPU was finished building those batches. So it finished all 3 batches, building them. And now as soon as our for loop says, okay, give me the next batch, you know, essentially this batch is being handed to the loop. This batch is still in reserve, and a new batch is being put in to replace the previous. So we're 2 ahead of ourselves at this point. So you can see how this prefetching helps prepare you. And once we've prefetched and filled our prefetch buffer, you can see now we're always, the CPU is still underutilized. The CPU could be doing other things if we needed it to. And remember, I have that sleep statement that's waiting for 1 second to simulate the training of the model on the GPU. So our GPU completes the training cycle, says, give me another batch. We build a prefetched batch after having handed it one of our pre-built batches. And then the CPU sits idle while the GPU is processing. The GPU comes back, says, I need more data. You're immediately ready to hand it a batch so that it can keep running while your CPU builds the next to buffer 2 in advance. And so you can see the benefit here of having the CPU able to process this data ahead of time for you. And this is a fairly straightforward data set. There's not a lot of processing going on. I'm not doing image augmentation at all, which is something you would usually be doing. So you could easily fill up this, the other half a second here on the CPUs with processing tasks. So keep that in mind. So we can go back. Are there any questions here? We can go back to the other question that Ray asked. Make sure you're on the O3 Pipelines for DL channel for Slack. Let's go back here. So, I mean, the reason for the breaks in the one we just looked at, the parallel version, was definitely because I have the sleep statement and the batch finishes processing. In this case, let's zoom in. See if it will show us what's taking. In this one, not quite. Oh, I see. Yes. So in this case, what's happening is, since it's all serial and there's no prefetching, everything is quote unquote synchronous. So when I call that, when I call the for loop, let me go back here to the script. So when I'm in the for loop and I call this iterative here, so when I try and ask for the next batch, there's not one just sitting and waiting for me. So the dataset pipeline has to run first, then it returns, and then it hits this sleep statement for a second. And so what you see here is a 1 second gap. So since it's all serial, that 1 second is explicitly here. Whereas in the parallel pipeline, my batches have been prefetched. So as soon as I call this, it almost immediately returns the data for processing, which I could then be passing to the model and crunching on the GPU, which is why this 1 second is immediately started. So this 1 second sleep is immediately hit. And then the prefetching for the next data set is what you saw happening in parallel to this sleeper here. So that's why you saw that dead time here. And so let's see if I can, before my 60 minutes is up on the, I'm gonna go in here real quick. I'm gonna see if I can just quickly change this without breaking things too much. If I can change this to 4i inputs and labels in enumerate train DS. I think that's consistent. Kyle, feel free to speak up if you see me doing something silly. Oh, right. I know why I did this. It's because of the profiler. Because I wanted the profiler to catch all of this stuff. Okay, well, anyway. So in principle, you should be able to do something like this, where you literally just iterate over the training data set and not having to do these silly iter and next, which is really, you know, in Python, anytime you do for, you know, X in some list, these are the underneath pieces that are being called to make it look pretty for you. So in any case, so I'm not going to show that live because the reason I did that was because of this call has to be wrapped around. But anyway, for the profiling. Okay. In the README, I also include a link to this repo, which is just I call it TensorFlow skeleton because it's the sort of thing where I just check it out whenever I want to start a new TensorFlow model, you know, training for any project, because it has the bits and pieces that I need to put together a workflow. And I include, for instance, the data handler here, explicitly the file that we saw there. So you'll see the get datasets. You'll see build dataset from file list, the one that we went over. You'll see, you know, loading the image and grabbing the label, grabbing the bounding box. So you'll see a lot of similar things here that you're familiar with. But I quickly threw in, because it's a personal thing, I don't really, not something I've farmed out or, you know, intended for a tutorial, but I quickly threw in some examples of how you might run to see ResNet run on the Imagenet dataset. So in the models, you'll see ResNet down here defined. And then you'll see where is it? It's in the configuration files, right? So this one. So this tells you what model you're using, kind of optimizer, and lots of other things, but then tells you which data handler. And so you should recognize this as well from the configuration file that I presented in the example. So this is really just cut out of this repo here. And if you're interested in playing around with a full example with ResNet, you should be able to run this on a ThetaGPU node and have that work. And if you can't, just email me with some questions and I'll see if I can make this a little more user-friendly, because really this is just something I use for my own. Okay, well, that's all I have. It's mainly to get you guys aware of parallel pipelines using these hybrid systems, where you've got computing resources of different types, and you need to think about how to use them to speed up your training loops. So, any other questions? It is the TensorFlow timeline, the profiler that I showed, is real time as far as I understand. And in my experience, it seems to map directly to runtime. So you can add printouts in places and verify that it's happening as it reports in the profile. The nice thing about it is that it also, as long as you have all the CUDA libraries loaded, captures all the GPU side operations too. So I don't know if one of my older ones has, let me see if I can bring this up quickly. When you have the GPU in the mix, it will look slightly differently. It'll separate out the CPU and GPU pieces. Yeah, here we go. So here's a parallel run. You can see the many parallel threads. But then you can see it separates out by device. So in this case, with this example, I don't have any machine learning components running. So really, whenever I ask for, you see these small slivers here, this is where it's saying, give me my next batch. And you see up here a copy to and from device. So you see the copying from the CPU memory to the GPU memory taking place as I request batches. And so it nicely separates that out. If I had a machine learning model running, you would see a similar stack up here, and you could see your convolutional layers, you could see your dense layers, your activations, and how much time is being spent in those things. So it's a very flexible tool, and I'm sure we will cover this in one of our following presentations. So I did include a link in the README, I think down here, on how to use it. Obviously, you can see in my example how it's being utilized. And then, I think in my TensorFlow skeleton example, it's actually a configurable command line option. You can tell it to turn on the profiling. And then which, that's for MPI stuff. And so there's an example there too. That's right. That's correct. So you can see in this example here, you can see how the timing, how they're synchronous here. And it's synchronized to that request for the batch. Any questions? We have time, so feel free to ask questions and don't be shy. We have myriad of levels of experience, and that is the point, is to give people the opportunity to have those online interactions that you might not get if you're just perusing technical websites. Okay, well, I will call it then. Feel free to still interact via the Slack channel. The data science group is from ALCF. We are always on and available there. So please reach out with your questions. Don't hesitate and take advantage of this opportunity. I wish there were such programs when I was a graduate student or an undergraduate student or in high school.